In this video, we will look at how Fourier series, which were developed to model periodic functions, can be applied to non-periodic functions, provided we are only interested in the behaviour of the function over a finite interval. We will also look at some examples which illustrate how making good modelling choices can improve the behaviour of the resulting series. We saw in my first video on Fourier series for periodic functions, how they can be used to express a periodic function as the infinite sum of trigonometric functions using the relationship shown here. This result can be generalized and applied to any function over a finite interval. In this case, it's irrelevant whether the function in question is periodic. However, unlike the periodic function case, the resulting Fourier series will not fit the function outside of the interval we used to derive the series. Let's start by considering a relatively simple function. Consider the function f of x equals x squared, defined on the interval 0 less than or equal to x less than 3. We can imagine a function that's periodic but matches f of x on the interval of interest. Here's an example of what I mean. Here I've taken the function x squared between -3 and 3, and then made g of x repeat over an interval of length 6. We see that the function g of x coincides with the function f of x equals x squared between -3 and 3, but nowhere else. We now generate the Fourier series for the periodic function g of x. First, we need to generate the Fourier coefficients an and bn, using an interval of length 6, i.e. setting L equal to 6. The formula for the an coefficients is 2 over L times the integral from -L/2 to L/2 of f of x times cos 2n pi x over L with respect to x. This gives 2 over 6 times the integral between -3 and 3 of x squared times cos 2n pi x over 6, i.e. 1/3 times the integral between -3 and 3 of x squared times cos n pi x over 3. Integrating by parts, we have 1/3 times 3 over n pi times x squared sine n pi x over 3 evaluated between 3 and -3. Minus 1/3 times 3 over n pi times the integral between -3 and 3 of 2x sine n pi x over 3 dx. Well, if we evaluate the terms in this first bracket, we get 0, since sine n pi is always 0. Thus, we are just left with minus 2 over n pi, integral between -3 and 3 of x sine n pi x over 3 dx. Integrating by parts again yields this result. Now it's the integral that's 0 because sine n pi is 0, and we're just left with evaluating 6 over n squared pi squared times x cos n pi x over 3 evaluated between 3 and -3. We have 6 over n squared pi squared times 3 cos n pi plus 3 cos minus n pi. And we know that the cos of minus n pi equals cos of n pi, thus this yields 36 over n squared pi squared times cos n pi, which can also be written as -1 to the n times 36 over n squared pi squared. For bn, we have the formula 2 over L times the integral between -L/2 and L/2 of f of x times sine 2n pi x over L dx, giving 1/3 times the integral from -3 to 3 of x squared sine n pi x over 3 dx. We could work through the integration again, but in fact we don't need to because we have an even function in this case which always yields 0 values for the b coefficients, i.e. we have bn equals 0 for all n. Thus, the Fourier series for the function f of x equals x squared is given by these formulae. Note that the formula for an only applies to positive values of n. The first term, a half a0, is the average value of the function x squared between minus 3 and 3, which is 3. We can examine the convergence of this series by looking at partial sums of the Fourier series, which are of the form shown here. Note that the sum here has only n terms, while the Fourier series has an infinite number of terms. Let's plot these partial sums to see what they look like. I'm only going to plot values between 0 and 3 in this case, since I know that both my original function and all of the sine functions are symmetrical about x equals 0, so we'd observe the same behaviour reflected between minus 3 and 0 as we have between 0 and 3. On the graph shown here, we see f of x plotted as the dashed orange line, and in green we see the first partial sum, corresponding to capital N equal to 1, which consists of these two terms. Next, we see the second partial sum, consisting of 3 terms, corresponding to capital N equal to 2. And the sum with n equal to 3, n equals 4, n equals 5, n equals 6, 7, 8, 9, and n equals 10. We observe that the partial sums approach the original function with only a few terms. We say the series is converging quickly. Looking at the formula for an, we see that the magnitude of the coefficient is inversely proportional to n squared, which is why the coefficients get small quite rapidly as n increases. Let's have a quick look at the coefficients themselves. Here we see the first 30 coefficients. It's worth noticing that the magnitude decreases more rapidly for small n, which means that once we get to larger n values, adding one more term to the partial sum provides only a small improvement to the approximation. However, we can, of course, take as many terms as we like to get to within a certain tolerance. Let's turn now to the function f of x equals x, defined for x between 0 and 3. This second example is nice and simple, but I include it to illustrate how our choice of periodic function can have a big effect on the behaviour of the resulting Fourier series. As before, we first imagine a function that is periodic, but matches f of x on the interval of interest. Here's one example where the periodic interval is of length 6. In this case, our periodic function coincides with the function f of x equals x between 0 and 3, but nowhere else. Alternatively, we could imagine another function that's periodic over the interval minus 3 to 3, but is discontinuous, such as the function shown here. This may have some advantages, as the behaviour of this periodic function matches that of the original function between minus 3 and 3. There are, of course, an infinite number of possible periodic functions we could choose, so I'm just going to pick one and say a bit more about how to make a good choice of periodic function to model f of x after we've done some analysis. Let's examine the second choice of periodic function shown here on the lower graph. Okay, so we need to generate the Fourier coefficients for our function g of x. We first look at the an coefficients. Well, L in this case is 6, so we have 1/3 times the integral from minus 3 to 3 of x cosine n pi x over 3 dx. This yields 0 for all n. Note that we could have deduced this directly from our knowledge of Fourier series, as odd functions always generate 0 an coefficients. We note also that the average value of the function is 0, so we also have a0 equals 0. Turning next to the b coefficients, we have bn equals 1/3 times the integral from minus 3 to 3 of x sine n pi x over 3 dx, which yields minus 6 over n pi times cos n pi. As before, the cos of n pi can be written as a power of minus 1, and we have minus 1 to the n minus 1 times 6 over n pi. Now we can examine the convergence of the Fourier series by looking at its partial sums, which are of the form shown here. I will again plot the partial sums on a graph to see what they look like, plotting values between 0 and 3. On the graph shown here, the linear function we are approximating is plotted in orange, and in blue we see the first partial sum. This consists of just one term, corresponding to capital N equal to 1, and the single function 6 over n pi times sine pi x over 3. Next we see the second partial sum consisting of two terms corresponding to capital N equals 2, and 3 terms, 4 terms, and 5. Skipping ahead to 10 terms in the partial sum, we see that the approximation is improving, especially close to x equal to 0. But the behaviour on the right is not doing much better than with 5 terms. This is because the value of our imagined periodic function jumps to minus 1 at x equals 3 and starts increasing again once we pass x equals 3. Thus our choice of periodic function has created a problem at the end of the interval. The same will of course be seen at x equals minus 3. Jumping ahead further to 20 terms in the partial sum, we again see an improvement in the approximation, but the discontinuity at x equals 3 still presents a problem. This error will decrease as we increase the number of terms, but the improvement is quite slow. Here we see the result for 30 terms in the partial sum, 40 terms, 50 terms, and finally 75 terms. We can understand the rate of convergence better if we think about the magnitude of the coefficients multiplying each sine wave, i.e. the Bn coefficients. It's clear that these are proportional to 1 over n, and thus the decrease in magnitude between one coefficient and the next is less rapid than for the first case we looked at. Let's look at the coefficients. Here are the values of the first 70. We can see that after the first few values, the magnitude of the coefficients decreases quite slowly, meaning that consecutive sine waves have a similar magnitude. This points towards the slow convergence of the partial sums. Looking at the higher values of n, for example those shown in the bottom row, we see the magnitudes of consecutive values decreasing very slowly as n increases. The wiggles and overshoot that we see near x equals 3 are a case of Gibbs phenomenon, which I discuss in my video on Fourier series for periodic functions. They arise due to the discontinuity at x equals 3. Knowing this provides us with a clue as to how to make a better choice of periodic function to model our original function. If we can avoid the discontinuity, then we should eliminate Gibbs phenomenon and get improved convergence. Going back to our original function f of x, we could have chosen the continuous even function I showed earlier. Here it is again as a reminder. This does indeed provide a Fourier series that converges much more quickly and eliminates Gibbs phenomenon. You might like to try plotting the first few partial sums of this for yourself as an exercise. In this case, the coefficients Bn will of course all be 0 because the periodic function g of x is even, and the average value of the function, a half a0, is 1.5. For the rest of the Fourier coefficients, the integrals need to be divided up, as g of x equals minus x between minus 3 and 0, and equals x between 0 and 3. Thus we have an equals these two integrals added together, yielding 6 over n squared pi squared times cos n pi minus 1. which can also be expressed as minus 12 over n squared pi squared for n odd, and 0 for n even. Plot the first few partial sums and see what you find.